So good morning, everyone. The next algorithm that we are going to explain is the link state algorithm. Okay, so link state algorithm is also a routing algorithm. We have already explained the distance vector algorithm. We have already explained, right? Or the Bellman-Ford algorithm we have already explained. Now, how is it different from the distance vector algorithm? Is that distance vector algorithm uses a distributed approach. Okay, whereas in link state algorithm, each of the routers will exchange the messages in order to get or know about the entire topology. So this is how it works. Okay, so it basically uses a greedy approach. Generally, this link state algorithm uses a greedy approach is what it uses. So let's see how this algorithm works. So link state algorithm, you all might know about a link state algorithm, which is Dijkstra's algorithm. Dijkstra's algorithm uses a greedy approach. It is one of the link state algorithm that we are having. We know that the Dijkstra's algorithm can be used for solving single source shortest path, that is given a single source, how to find from that particular node the distance to all other possible destination, right? So it finds the shortest path from one particular source node to all other remaining nodes of the graph. So this is what it does, right? Now let's see what are the conditions. So Dijkstra's algorithm or link state algorithms work only for connected graphs. And Dijkstra's algorithm cannot work for negative edges. We are not implementing for negative edges. And also we can implement this algorithm for both directed and undirected graph. These are some of the conditions that we have to know before we start this particular algorithm. So over here, the algorithm, I'll just explain the probable, like what all other thing, what all other matrices that we have to use and all. Then we'll move on to the explanation by using an example. So by means of distance, I have a distance array called as dist is what is taken. So dist of s meaning distance from source to itself. Okay, so this distance array is what I'm using in order to store the distance to all other nodes. Okay, so distance of S meaning distance from source to itself. When I say distance of 1, it means distance of 1 from source. Okay, so from the source is what we are calculating. Okay, so and then I am maintaining a predecessor list, which I initially nothing is there, so I'm keeping it as nil or null. Nothing is there. Then this is how we start the algorithm. We just add first source to the node set. So we maintain a node set wherein we keep adding, finding the best possible path. Okay, so that particular node information or the least cost information is what we keep on adding. So except the source, for all the nodes, this is what we do. I am initializing the distance from source to V, node V, where V can be 1 to n minus 1, except the source. We are just keeping everything as infinity, and the predecessor list we are actually initializing it as nil. Okay. Then initially nothing is added to the node set, so I'm keeping S as equal to null set, and we are adding, the next node which we are taking into consideration is V. So as long as V is not equal to null set, what we are doing is we are finding from the source, we are finding which link is the least connected component. Okay, so how do I know the least connected component? It should have a least distance. So that is why we are doing minimum distance of q comma distance we are doing. So if you find such a u, you add that to the node set. S we are adding. Then, with the knowledge of the node U, which we have just now added, we are just trying to find what will be the distance of any particular node V from the source. So this is how we calculate. If the direct distance is minimum, we take that, or if through the node U which you have found just now, if that distance is minimum, then we have to choose that. So that is why we have written here distance of V, if it is greater than distance of u plus distance of plus cost of uv, then we update the distance as equal to distance of u plus cost of uv. W of uv is nothing but the link cost information, and we return the distance. So this is how this particular algorithm works. Now let me explain by means of an example for your better understanding. So let us consider this as the topology, and What we do is that, you know, that in this particular thing we have S, A, B, C, D, E. We have 6 nodes we have in this particular topology, and the cost information is also displayed here. Step one, what we do, we are creating two sets. First, I told you d of s we initialize it as equal to infinity, and s we initialize to null, or visited set we initialize to null set, right? So we are having all these nodes have to be visited, or it forms unvisited set s, a, b, c, d, e, and visited set is equal to null. Step two, what we do is we are just initializing, like how I explained in the algorithm. The predecessor list of each node, we are initializing it as equal to nil, and the distance from source to itself is equal to 0, and we are maintaining the distance of any node to the source, or from source to any node, as equal to infinity before we start that call. Step 3, what we do, we start off with the source vertex. So vertex S is what is chosen. Now S is added to the node set. Okay, so now after that what we do is, if you see the topology, these are the two connected components that I'm having. So from S, A is at a distance of 1, and from S, the B is at a distance of 5. You can see here, correct? Now what I do is that I had already updated dA, that is dA meaning distance of source to A, as equal to infinity was what I had initialized, and also distance of B from source I had initialized it as infinity before. But now when I analyze the connected components, what I do is I have to find the U part, the U node, the first node from source, which is at a least cost, is what I'm trying to find. So when I find that, when I analyze the connected components, you can see that A is the least connected component. I told you it is a greedy approach that it takes. So it takes the least cost path. It is least cost path is what it takes. So dA is equal to 1. So since it is lesser than dB, which is 5, okay, so what we do is that the predecessor list of S, I keep it as equal to A. Okay, or sorry, predecessor list of A, I keep it as equal to S, the predecessor node. So from S to A is what we are doing. Okay, so coming to the next slide. So we did this part. Now A is the one which is chosen. Okay. So from A, you analyze the least, the connected components. So the connected components are to C at a cost of 2, to D at a cost of 1, to B at a cost of 5 we have, 2 we have, right? Now you have to find, with the knowledge of A, does the distance to all this change or not, we have to find. So I've just shown the calculation here. You can see that distance from distance of C, it was equal to infinity. Now A is advertising a cost of 1 to source is what it is advertising. So what we do is that we add the link cost. So 2 is the link cost to it, plus 1 is a cost which is getting advertised, giving a total cost of 3. So DC, prior it was infinity, now it will get updated to 3. Similarly, D, when we are taking, initial cost of D was infinity. Now A is advertising that to source node S, it can reach at a cost of 1 is what it is saying. So now I add the link cost of it. So A to D is 1, plus distance from source to A, D of A is equal to 1. So when I add this, I get distance of D, or to the node D is equal to 2. 2 is anyway, comparatively 2 is minimum when compared to, infinity. So we do the updation of the distance of this as equal to 2. Same way to B. Okay, B initial cost was 5. The direct cost from S to B was equal to 5. That is what was updated. Now with the knowledge of A, we are trying to find. So when I add the link cost, I get 2 plus 1, 3, which is a least cost compared to 5. So I update the distance vector as equal to 3. Okay, so this is how we are doing the updation. And now what we do is that out of this, you have to find the least cost which you have found. So DC is 3, DD is 2, DB is 3. So the least cost information is 2 is what is the least cost information, right? So you have to choose, the next step is that you have to choose vertex D is what you have to choose. Okay, so when you're choosing vertex D, what we do, We have to find, with the knowledge of vertex D, we have to find the shortest path to all the other nodes we have to find. So when we are finding this part, okay, when we are finding from D, when we are choosing the part, you can find, you can see with, I'm just trying to find the connected components. This is where the connectivity is important. So D is connected only to E. Initially, previously the cost was infinity. Now when I find what is the cost that I'm having, you can see that with D is advertising a cost of 2 is what is advertising. My link cost is how much? 2. So DE will be updated as equal to 4. Okay. And DD, so this is how we are actually maintaining the information. So now out of this particular given graph, which all are the nodes which are added? S is added, A is added, D is added. Now the unvisited nodes are B, C and E. Out of this you have to find the least cost. So here we are having B and C at a cost of 3 is what we are having, and E is a cost of 4 is what we are having. So either you can choose B or you can choose C because it is the same distance, right? Least cost distance, next least cost distance is 3, which is either B or C. I am choosing B since I am going in a chronological order. I am going. You can if you want you can choose the other one also. C also can be chosen. Now dB, when we are finding, you can see that when I'm calculating dB, sorry, just observe on this picture, when I'm calculating dB, you know that with the knowledge of D is what? It will not affect because I don't have a, a connected component I don't have. So dB, there is no change. So I add B also to the visitor set. Next, we have to choose C. Now, when you choose C, you can see that the C is advertising a cost of 3 is what it's advertising. Okay. Now E will add the link cost to it. So 3 plus 1 is equal to 4. The previous distance of E was also equal to 4. Okay. So what it does is that since it is not able to find a better route, it just maintains the same information. So the unvisited set now is only E, and all other sets are visited. Now vertex E, the last one, when you are implementing, it will be automatically added. Vertex E is the one which is chosen. Nothing is there to be relaxed or to find the shortest path. So we just add that also to the node set. Now all the vertices of the graph are processed, and our shortest path route will be looking like this in the form of a tree. The order in which the vertex are processed is S, A, B, A, D, B, C, E. This is how the vertex are processed. Okay. Now, in order to show you the execution of it, I am taking a smaller topology. This is the topology that I'm going to take in order to show the execution of the program. So over here you can see X I'm taking it as node 1, Y I'm taking it as node 2, and Z I'm taking it as node 3. Okay, so the distance information is given here. This is what I'm going to show you for the execution part. So now I'm going for the execution part. I'm stopping the share of this and sharing the terminal for execution. So over here you can see that I'm just showing the execution. Okay, so I have this program. So cc link state.c, okay, for compilation, and I'm just executing using ./a.out. The number of nodes it is asking, so I'm giving it as 3. The cost matrix, the last cost matrix which I have taken is 0, 1, 5, okay, 1, 0, 2, and 520. This is the distance information that I'm having. It will ask you to enter the source matrix. I'm adding the source matrix as equal to 1 in our example as x. So you can see that it has found the shortest path. 1 to 2, the shortest cost is equal to 1. X to y, the cost is equal to 1. And x to z, you see it has got updated, the cost is equal to 3. So this is how you execute this particular program. Thank you.